In the last video, we introduced the DFT, the Discrete Time Fourier Transform. DFT is a nice tool that enables us to get the frequency content of a discrete time sequence. The output of DFT is periodic and continuous, and the frequency content of the signal is confined within only one period, which is 2π interval. Being continuous in the frequency domain, the DFT is defined over an infinite range of frequencies and requires an infinite number of computations to evaluate. This is not feasible in a computer with finite memory and computation resources. Computing the DFT requires performing an infinite number of complex multiplications and additions, which makes it computationally expensive and time-consuming. With the increased use of digital computers and specialized hardware in digital signal processing, interest has focused around transforms that are suitable for digital computations. The Discrete Fourier Transform (DFT) is a practical tool that can be used to analyze the frequency content of discrete time signals. The DFT is defined on a finite number of samples and can be computed efficiently using the fast Fourier transform algorithm, which is much faster than computing the DFT directly. Today, we will introduce the concept of DFT, and in the next video, I will discuss the most efficient algorithm to compute the DFT, the fast Fourier transform (FFT). Suppose we have a discrete complex exponential signal in that form, with n and k are integer values from 0 to m-1. Let's set m to be 8 sample points. If k equals 1, then at n equals 0, the function represents a complex number in a polar form, represented in a complex plane as a vector with magnitude of 1 and angle of 0. At n equals 1, the function is a complex number with magnitude of 1 and angle of π/4, 45 degrees from the real axis. It can also be represented in a rectangular form using Euler's formula as a complex number with real part of 1 and an imaginary part of -1. At n equals 2, the vector is having a magnitude of 1 and phase of π/2. At n equals 3, the vector is at 3π/4, which is 135 degrees, and so on. Notice that the angles are moving in a clockwise direction as a result of this minus sign. From the graph you can see that we divide the 2π angle, or the full cycle, over m sample points, which is 8. It can also be shown in the complex exponential formula. So when k equals 1, each 8 sample complete one full rotation. Now we stop at n equals m-1, which is 7. If we increase n further and further, we get new points in the same locations we got before. In other words, this is periodic complex exponential signal with period of m samples. Now this is not the complete picture. This is just the front view of the discrete complex exponential signal. Here's the discrete complex exponential with the third axis representing n. The front view shows the complex exponential samples in the complex plane. The top view shows just the n-axis and the real axis, representing the real part of the complex exponential, which is cosine from Euler's formula. The side view shows n and the imaginary axis, and representing the imaginary part of the complex exponential, which is sine from Euler's formula. Recall that k equals 1. If we make k equals 2, this changes this quantity from 2 pi over 8 to be 2 pi over 4, increasing the angular frequency. So instead of 8 samples complete one full rotation, now only 4 samples completing one cycle. The period became 4 samples. This is also can be shown in the formula. 4 in the denominator means the period is 4 samples. So the 8 samples now complete 2 full rotations. The first sample is at angle of 0, the second is at pi over 2, the third is at pi, and so on. If we increase k further and further, the frequency of the signal increase. For instance, if k equals 3, the 8 samples complete 3 full cycles. When k equals 4, the 8 samples complete 4 cycles. After 4, the frequencies start to decrease as a result of aliasing. I discussed aliasing in the complex exponential video. I also have a separate short video for aliasing. We can also plot the function versus k at a specific n value. For instance, at n equals 1, the discrete complex exponential can be plotted versus k, one sample for each value of k, where k is integer from 0 to n minus 1. If we increase n, the speed of rotation increase, since the angle of each sample increase. The plot versus n is called the discrete time domain, while the plot versus k is the discrete frequency domain. You can think of k as the discretized frequency, while n is the discretized time. Now suppose we have a discrete complex exponential in a frequency domain, having that form, and plotted versus k. As we change n, the period change. And here's another complex exponential with magnitude of 1 and n of 1. If we add them together, we get different function. We can add to them another complex exponential with n of 2 to get another different function. We can add another one with n equals 3. Four, 5, 6, and so on. Being a summation of complex exponential functions, the resultant is also a complex function having real and imaginary parts. The top view represents the real part of the resultant, while the side view represents the imaginary part. The front view is showing the resultant in a complex plane, or the polar plot. Here is the resultant, as well as its front, top, and side views. This is the main idea of discrete Fourier transform, a summation of discrete complex exponential signals. If we have a discrete signal in time domain, plotted versus n, with finite number of samples m, then each sample in the signal can be represented in the frequency domain as a discrete complex exponential with the same number of samples m. Here m is 4D samples. We will see shortly why this is true. Just trust me for the time being that each sample corresponds to a frequency domain complex exponential in that form. The magnitude of the complex exponential is the value of the sample itself, while n of the complex exponential is the index of that sample. If we sum all of these complex exponentials associated with each time domain sample, we get the frequency domain representation of the signal. Notice that all the complex exponentials here, as well as the resultant, are plotted versus k, the discrete frequency. The time domain as well as the frequency domain are discrete, meaning we can store and process the signal in a computer. M is equal to 4D, meaning the time domain signal is consisting of 4D samples. Also, the frequency domain complex exponential associated with each time domain sample is consisting of 4D samples. That means that the summation of them, or the frequency domain, is also made up of 4D samples. Even though the time domain has 4D samples, only the samples from -6 to 6 are taken into consideration. The rest of the samples have a value of 0, meaning the complex exponential associated with each one of them have a value of 0. Once again, the time domain as well as the frequency domain are discrete, and this is the advantage of discrete Fourier transform. The time domain is a rectangular function, and the associated frequency domain is sinc. This is the analysis formula of the discrete Fourier transform. It takes the discrete time domain signal to give the frequency domain representation of it. The DFT analysis formula is telling us that if we have a discrete time signal, then each sample in the signal is associated with periodic complex exponential in the frequency domain with magnitude equal to the value of the sample and n equal to the index of the sample. Just sum all of them to get the frequency content of the signal. The synthesis formula of the discrete Fourier transform is doing the opposite. It takes the frequency domain signal to give the associated time domain. The synthesis formula is also called inverse discrete Fourier transform. If we have a frequency domain signal plotted versus k, each sample in the signal can be represented in time domain as a discrete complex exponential with the same number of samples m. The complex exponential associated with each sample is having that form. The magnitude of the complex exponential is the value of the sample itself, while k of the complex exponential is the index of that sample. We can sum all the complex exponentials associated with each sample in the frequency domain signal, and the resultant is representing the time domain. Don't forget that the time domain is plotted versus n, while the frequency domain is plotted versus k. Notice that each complex exponential associated with each frequency domain sample is scaled down by the number of samples. Here we will take the 4D samples into consideration, since most of them have non-zero values. Inverse discrete Fourier transform is doing the same process as the discrete Fourier transform, a summation of discrete complex exponentials. But in the inverse discrete Fourier transform, each complex exponential is in time domain, meaning plotted versus n, and scaled down by the number of samples, which is 4D in this case. Also, the complex exponentials have positive exponents, unlike those in the forward DFT. Recall that m is equal to 40, so the frequency domain sequence is 40 samples. The time domain complex exponential associated with each sample is consisting of 40 samples, and hence the summation of them, which is the time domain, is consisting of 40 samples. So the inverse DFT is just a summation of m periodic discrete complex exponentials, just like the DFT. That's why the summation limits are from 0 to m-1. As you can see, the DFT provides a fixed frequency resolution that is determined by the length of the signal being analyzed, m number of samples. This can be useful in some applications where a specific frequency range needs to be analyzed with a specific degree of precision. In contrast, the DFT provides a continuous frequency spectrum with infinite resolution, which can be more difficult to interpret in practice. So the DFT can be easily implemented in software using any programming language. Just by summing all the time domain complex exponentials associated with each sample in a frequency domain signal, we got the time domain rectangular function we started with. The discrete Fourier transform is a mathematical tool used to analyze and synthesize the frequency content of discrete time signals. The DFT analysis formula calculates the frequency components of the signal. The DFT synthesis formula reconstructs the signal from its frequency components. These formulas are fundamental to digital signal processing and are used in a wide range of applications, including audio and image processing, communications, and control systems. In the next video, I will discuss how to compute the DFT and how the FFT proves a much faster and more efficient way of doing that.